Welcome to the lecture series on superconducting resonators. This series is brought to you by the NYU Nanolab, the Laboratory for Quantum Materials and Devices. We would also like to give special thanks to the NordTech Hub and the Microelectronics Commons for making this lecture series possible. In this presentation, we'll demonstrate how to properly simulate your designed quantum circuit and extract the model into GDS file. As a goal of this part, we will show how to import your already designed quantum circuit into 3D electromagnetic solver, HFSS, properly simulate the eigenmode and driven mode of the design, and in the end, extract the design into a GDS file. In the last video, we designed a simple quantum chip resonator using Qiskit Metal library. As future designers, it's essential to evaluate your chip with powerful tools like HFSS. This simulation software allows you to extract key parameters, such as the coupling quality factor and resonance frequency, with high precision, which is critical information for guiding your fabrication goals. It also helps identify potential shortcomings or design mistakes early on, preventing costly errors down the line. Keep in mind, this tutorial builds directly on what we covered in the previous session. If you haven't watched that video, or if you'd like a quick refresher on the design process, be sure to check out our introduction to Qiskit Metal before continuing. Let's talk more about HFSS. HFSS, or High Frequency Structure Simulator, is a 3D electromagnetic solver developed by ANSYS, and it's one of the most powerful tools available for analyzing microwave and quantum devices. In this video, we'll focus on two types of simulations: eigenmode and driven mode. In an eigenmode simulation, no external signal is applied. Instead, the solver calculates the natural electromagnetic modes of the structure directly from Maxwell's equations. This tells us the intrinsic resonance frequencies and field distributions of the resonator, independent of any input or output. Driven mode simulation, on the other hand, introduces excitations through external ports. This allows us to study how the structure responds to a real signal, letting us extract quantities like S parameters and visualize field propagation along the feed line. So why S parameters? They are the standard way to describe how energy flows through a microwave device, or better to say, how much power is transmitted, how much is reflected, and at which frequencies resonance occurs. By combining eigenmode and driven mode simulations, we get both the fundamental properties of our resonator and its practical response when connected to measurement equipment. Now, let's switch back to the VS Code environment, the place where all the magic happens. This session won't involve much coding in contrast to the last video. It's mainly about launching and running the simulation through our Python script. Remember, HFSS is a very advanced tool, capable of handling a wide range of simulations across ANSYS software. In this tutorial, we won't be covering how to set up HFSS from scratch or walk through its interface. What matters here is that your system has the proper license, and that HFSS opens without any issues. And just as a lighthearted reminder, you can't make popcorn without a microwave, so make sure your HFSS is ready before proceeding. Just a quick reminder, the code we're running here needs to come right after the code from the previous video. That's because it's using the same variables we already set up, so make sure you've got those in place before running this part. Let's continue our block adventure by moving from layout design to simulation setup. First, we instantiate HFSS renderer with HFSS_renderer. This tells Qiskit Metal that we want to use HFSS backend to prepare and export the geometry. Next, we start the simulator with start command. This launches ANSYS Electronics Desktop, opens HFSS, creates a new project, and establishes a live connection with the notebook. From here, the chip layout in Qiskit Metal can be exported directly into HFSS. Here, we create a new design inside the newly created project and link it directly to the renderer we already set up. The new ANSYS design command does the following. First, opens a new HFSS design within the ANSYS Electronic Desktop, also known as AEDT session. Second, names the design. For now, let's call it Resonator EigenSim. And third, sets the solution type to eigenmode, which is used to compute the natural resonance frequencies and fields of the structure without needing external excitations. After running this, the design window opens in AEDT. Time to transfer the design from Qiskit Metal layout into HFSS. Render_design function is the command to do so, with the following variable to be defined. Selection gives the option to select specific components for rendering. If left empty, the whole design is rendered, which is something we are looking for. Open_pins, used when you want to leave certain pins open in the HFSS model. Here, no pins are left open. Port_list defines lumped ports in the simulator. Each tuple specifies the components, port_1 or port_2 here, the pin type which is in, and the port impedance which we desire 50 ohm. Box_plus_buffer disables the automatic buffer that HFSS adds around the chip. This ensures that the simulation box exactly matches the chip size we defined earlier. After running this command, HFSS will display the chip layout with the ports placed at the launch pads, ready for defining boundaries, meshing, and running electromagnetic simulations. Now we configure the Eigenmode simulation setup. This defines how HFSS will solve for the resonant modes of our design. Names the simulation setup so it can be easily identified. N_modes tells HFSS to solve for the first eigenmodes, or in other words, resonance frequencies of the structure. Here we set it to 4, even though we have only one resonator. You're going to see why. Max_passes sets the maximum number of adaptive mesh refinement passes simulator will perform. More passes improve accuracy but increase simulation time. Delta_f, the frequency convergence tolerance, in megahertz. This means the solution refines until the resonant frequency change between passes is less than 2 MHz. Min_converged specifies the minimum number of converged passes required before HFSS accepts the solution as valid. Let's go by 3 for now. This setup ensures that the Eigenmode simulation will run with sufficient refinement to find the resonance frequencies and field profiles of the resonator design. By balancing delta F and max passes, you can trade off between simulation accuracy and runtime. Time for launch. This command starts the Eigenmode simulation using the setup we defined earlier. Have in mind that the system will automatically define the mesh for simulation based on Qiskit's mesh settings. You can add your own preference for mesh setup inside the software. It instructs HFSS to run the Eigenmode configuration, perform adaptive meshing, and calculate the requested number of eigenmodes. Once the simulation finishes, the simulator provides the resonance frequencies, quality factors, and field distributions of the design. Now let's wait a couple of minutes, and in some cases, hours. These simulations could take long enough to make you older, so just be patient with them. For the sake of the video, we will not put you behind a screen that long. Okay, it's done. Let's dive into the results. By right-clicking on the results section and plotting the eigenmodes, you are able to see how the simulation converged and whether it was successful or not. Make sure that you select the simulated eigenmode as the option. And do the same thing for quality factors plotting. This is the convergence plot for the quality factor. As you can see, there is a jump for Mode 2 and Mode 4, which is a significant change, and this will be a question for further studies why such a jump occurred. This plot shows how the eigen simulation converges. If you see that the convergence is not good enough, rerun the simulation with a higher number of passes and hope for the best. For this specific circuit, we are seeing that 4 modes are converged properly in the Eigenmode results. But in quality factors, there is a discrepancy that should be studied. Since we targeted 5 GHz as a target frequency, we are expecting mode 1 to be the mode we are looking for, which is the one closest to the desired number. But there is a better way to make sure. HFSS will give us the option to see the electric field distribution. By running the command plot _ fields for the main structure, the simulator will calculate the fields and plot it on the schematic. By default, it will plot mode 1. Look at the fields near the resonator. It's a good sign. The first mode of resonance is coming from the built resonator coupled to the main transmission line. For just making sure, let's investigate where the rest of the resonances are coming from. To change the number of modes to see where the rest of the modes are, just change the source of the electric field distribution. Here let's change it to the second mode. For changing, we need to set the amplitude of the current mode to 0 and set the desired amplitude to 1. Here, it would be mode 2. And not forget to update the plot. As you can see, the second mode of natural frequencies is coming from the main transmission line. Be aware of such natural frequencies and make sure they don't interfere with your desired resonance frequencies. Let's check the third mode. You can see that the resonance is coming from the second mode of propagation in the resonator. Based on previous videos, you can explain what it actually means in a half-wavelength resonator. Time for fourth mode. The same as the third mode. The fourth mode is showing the third mode of the propagation in the resonator, which is already too high and above 10 GHz. So we can be somehow assured that the design is free of extra and disturbing modes of frequency. It's time for the next type of simulation, which is the driven mode simulation. So let's go back to the code. In this type of simulation, it is possible to simulate a S-parameter sweep along the desired frequency to determine the reflection and transmission of the quantum chip. Scattering Impedance Sim library imports the scattering impedance simulation class from Qiskit Metal, which is used to calculate S-parameters of the design. Let's do a quick recap. S-parameters, or scattering parameters, describe how microwave signals travel through and interact with a circuit. S11, or reflection, shows how much of the signal sent into port 1 reflects back. S21, or transmission, shows how much of the signal sent into port 1 passes through to port 2. S12, S22 describe transmission or reflection in the opposite direction, or at the second port. These values are expressed as ratios of outgoing to incoming wave amplitudes, usually in dB. When a signal passes through the feed line coupled to a resonator, at resonance, energy is stored in the resonator, leading to a dip in S21, which is a sign of less transmission, and a corresponding change in phase. Away from resonance, most of the signal passes through with little disturbance. Here, we create a scattering impedance sim object called driven mode, which connects our Qiskit Metal design to the HFSS backend. This object manages the process of running S-parameter simulations, allowing us to calculate how signals reflect and transmit through the chip. Next, by assigning HFSS_driven mode, we directly store the HFSS renderer inside a variable. The same as the Eigenmode part, this command activates a design inside the driven mode project, named as driven_sim. As you can see, instead of Eigenstudy, the mode of simulation is set to hybrid mesh refinement, which is the driven mode simulation that we are going to use. Similar to the earlier explanation in the Eigenmode part, this step transfers the entire Qiskit Metal layout into HFSS, but this time for driven modal simulation. Since it is covered once, we just run this block. This block adds a frequency sweep to the driven modal simulation in HFSS. Setup_name refers to the driven modal setup where the sweep will run. We will go by the default name, which is setup. Name equals sweep, the sweep's label inside HFSS. Start_gigahertz and stop_gigahertz defines the sweep frequency range. Based on the Eigenmode results, we are looking for a resonance near 4.6 GHz, so let's set the range from 4.5 to 4.7 GHz. Most of the time, it is needed to run the simulation again for the smaller range, which is something we will do now. Count number of frequency points in the sweep, giving a fine resolution, approximately 660 kHz steps for now, which is 301 points. Don't increase this number too much because it might fill up your RAM and your simulation fails. Type equals interpolating, uses HFSS's interpolating sweep method, which reduces simulation time by solving only selected points and interpolating the rest. Here are the variable we set for sweep, just for confirmation. Since we want to proceed with the results of the Eigenmode, it is needed to keep the mesh structure proposed in that simulation. So it is highly recommended to import the mesh design of the Eigenmode to the driven mode simulation. By clicking on the properties of the simulation setup and going to Advanced menu to use the same Eigenmode project, you will successfully add the previously designed mesh and solutions to this simulation. This will help your consistency. For just making sure, we will ask the simulation to rerun the Eigenmode if it is needed. And again, rocket launch time. Analyze_sweep command runs the frequency sweep we just defined. Now the simulation is done. Let's plot the results. As you can see, we find the peaks we were looking for, but they are not sharp enough and we need a higher resolution. Now that we know the position of the peak, let's decrease the range by 100x, so the resolution improves by far. So let's define another sweep command, sweep_optimized, with the same settings except the frequency range. This time, let's run it from the software by just clicking Analyze in the Setup section. Since the mesh is already assigned, this round will be shorter. For doing any interaction with the software, we need to save the file, so let's save it quickly. And again plotting, but this time we plot sweep optimized results. Looks much better now, a resonance frequency in the end. So our resonator chip is working properly. After finalizing the design by doing electromagnetic simulations, we can proceed by exporting the GDS file of our design. Back to Qiskit Metal GUI. By pressing the GDS button on top, the software will allow us to export the design GDS file by editing the file in design or dimensions, which is preferred. For just exporting the design, the basic settings will work. GDS files can be opened with Klayout software, which is an open-source design editor software that you can use to edit your design further or customize it manually. And that's it! Your design is ready to serve. So let's take a step back and review what we've covered in this session. First, we walked through how to properly send a design into HFSS, making sure that everything transfers smoothly without errors. Next, we explored how to simulate our design both in Eigenmode and driven mode, this time from the coding environment rather than the graphical interface, giving us more flexibility and automation. And finally, we discussed how to extract our finalized design into the GDS format, which is the key step for moving from simulation to actual fabrication. Altogether, these steps give us a complete workflow, from design transfer to simulation, and finally, to fabrication-ready files. Thanks for your attention.